Be taking physical chemistry one, that is with respect to thermodynamics and chemical kinetics, that is of unit 1 and 2. So in this we are going to study the basic terms and principles of thermodynamics and the first, second, and third law of thermodynamics. And in the second block, we are going to study about the chemical kinetics, fundamental techniques in the chemical kinetics, and rate constant, half-life period, and deviation of total order of reaction. This we are going to study in the second unit. So coming to the first part of the basics of thermodynamics. Here some of the basic terms are given. So first we should be knowing what is thermodynamics. So thermodynamics is the flow of heat. So here we are going to study the energy and energy of transformation and relation to its matter. So thermodynamics means the flow of heat. It is study in the request ಕಳಿಸ್ತಾ ಇದ್ದಾರೆ. So the study of physical and chemical process may be approached into two different ways. So here one is canonical theory, which is used for the study of thermodynamics, and next is the thermodynamic approach. So two different theories we are going to study in the canonical theory approach and thermodynamic approach. So in canonical theory approach, it concerned with the process which may be treated in terms of atoms or molecules. So in thermodynamic approach, it concerned with the energy, the charges involved in the system. So we are going to study with the system, the number of charges present in the system. So we are going to study the reaction taking place. So these are the two different methods. And coming to next, the study again, the thermodynamics, the study of energy, the energy of transformation, and its relation to matters. Here we are going to study three different laws, that is zeroth law, first law, second law, and third law of thermodynamics. So, and before getting into the topic, we should be knowing some of the basic terms. So, in the first, some of the basic terms used in the thermodynamics are system, surroundings, boundary, process, state, and equilibrium. So these are the some of the basic terms we are going to use in the study of the thermodynamics. So coming to the system, system is nothing but where the reaction is taking place with respective of surroundings, and the system is concerned with some boundaries. So a quantity of matter or region in a space for the study, chosen for the study, that is known for system. So there are three different types of systems. One is isolated system, open system, and closed system. So the word itself will be knowing the meaning of that. So what is isolated system here? A system which can exchange neither energy nor matter with the surrounding. That is the isolated system. For example, hot water kept in the thermo flask and ice cream kept in the refrigerator. So these are the example for isolated system. So these are the important terms what you are going to study in the thermodynamics. So isolated system means a system which can exchange neither energy nor matter. So that is the isolated system. And next is the open system. Open system is a system which can exchange both energy and matter with its surroundings. So, for example, if you are taking the system with the surroundings, both the thermal energy, pressure, everything will be exchanged with the surrounding. That is the open system, a system which can exchange both energy and matter with the surrounding is called open system. And next is the closed system. Closed system is the system which can exchange energy but not matter. It can only exchange energy, but matters cannot be exchanged. That is the closed system. So here three different system where they are given the this is the for isolated system, this is the open system, and this is the closed system. So here in the isolated, what is happening here? No matters can be exchanged. Only matters or energy can be exchanged, either matter nor energy. So in the open system, both energy and matter can be exchanged. In the closed system, no matter or energy can be exchanged. So this is the figure where they are explained graphically. Coming to the next, depending on the chemical composition and physical properties, the substance present in the system are classified into two types, such as homogeneous system and heterogeneous system. So, what is homogeneous system here? A system is said to be homogeneous when it's completely uniform throughout the system. So, that is known as homogeneous system. Chemical composition, physical properties are some of the uh, properties where it is completely uniform. So that is known as homogeneous system. And coming to heterogeneous system, where it is not uniform. So it is an opposite of homogeneous system. It consists of two or more homogeneous bodies. So it won't be in the uniform state. That is known as heterogeneous system. And for example, water with ice floating in its example for heterogeneous simple system. And next is the state function or state properties. So the various properties that can be quantified without disturbing the system are called function or state function. So for example, internal energy, pressure, volume, temperature. The state function means the various properties that can be classified without disturbing the system. For example, it won't disturb the system. Now, what we have seen in the previous images. So, for example, it may be internal energy, pressure, volume, or temperature. And next is the state variables. And state variables, the measurable properties required to describe the state of a system are called state variables. For example, pressure, temperature, volume, mass, composition are the important state variables. And with respect to the properties which is associated with the collective behavior of the properties are also known as macroscopic system. For macroscopic system, the examples are fixed amount of liquid gas, which is having pressure, volume, and composition, density, and refractive index. So it can be the example for macroscopic system. And next is the state variable. There are two types. One is independent variable and dependent variables. So a state variable which depends on other variables is called as dependent variables, and which is independent are known as independent variables. So variables are nothing but here pressure, volume, composition, internal energy. So these are the variables which are not dependent. That is known as independent variables. So based on the system, State variables are classified into three different types further: extensive variable, intensive variables, and specific variables. And coming to the extensive variables, state variables whose value depend on the size of the system. So here the size of the system also matters. So that is denoted by extensive variables. So for example, it depends on the size of the system varies, means the volume and the mass energy also varies. And next is the intensive variables. Intensive variables whose values does not depend on the size of the system. For example, mass intensive variables will be, ಈಗ ಸಿಸ್ಟಮ್ ಅಲ್ಲಿ ಇಂಟೆನ್ಸಿವ್ ವೇರಿಯಬಲ್ ಡಿಪೆಂಡ್ ಆಗಲ್ಲ ಅಂದ್ರೆ ಇಟ್ಸ್ ಓನ್ಲಿ ವಿತ್ ದ ಡೆನ್ಸಿಟಿ ಆಫ್ ದ ಮಾಲಿಕ್ಯೂಲ್ಸ್ ಆರ್ ಆಟಮ್ಸ್. ಸೊ ದಟ್ ಈಸ್ ದ ಇಂಟೆನ್ಸಿವ್ ವೇರಿಯಬಲ್ಸ್. And coming to the examples for extensive variables, ke yeah, the examples andre it may be mass and volume. So it definitely varies with the size of the systems. Size of the system vary ಆದಂಗೆ mass and volume of the con- molecules also vary. So where it does not reflect on the density of that molecules. So this is with respect to intensive and extensive variables. And next is the specific variables. Specific variables, if the extensive variables are expressed per unit mass of the system, that is known as specific variables. With respect to unit mass, if it is expressed, that is known as specific variables. And next is the state functions. State function, so these are the important terms what you are going to use in the further in the studies. So the state functions is the state function is a property of the system whose value depends only on the state of the system. So in, yes, and state functions. The state function is a property of the system whose value depends only on the state of the system. For example, pressure, volume, temperature, internal energy, enthalpy, entropy are the state functions. So here, even in the next step, you will get to know what is state. So state of the system is the defined by its variables. So uh, pressure, temperature, volume, these are the variables, and we are going to study. And further, a system consists of large number of particles such as atom, molecule, etc. In the system. If it shows whole system to be studied in a time, then it is called as macroscopic system. So we are going to study in a system with respect to pressure, temperature, volume, where with reaction of atoms and molecules in a system. So coming to the next is the thermodynamic equilibrium, a system in which macroscopic properties do not undergo any changes with time. With time is said to be thermodynamic equilibrium. So there will be no undergoing any changes with time. For example, there are three types of equilibrium. One is thermal equilibrium, mechanical equilibrium, and chemical equilibrium. So first is the thermal equilibrium, where there is no flow of heat. Thermal itself, thermal equilibrium andre, where there is no flow of heat in one position of the system to another. The thermal heat is not flow. The flow of heat is not there. So that is known for thermal equilibrium. And next is the mechanical equilibrium, where the system is said to be mechanical equilibrium if no mechanical work is done by the system. So this is known as mechanical equilibrium if the system is not moving or if there is no mechanical work is taking place inside the system, that is known as mechanical equilibrium. Next is the chemical equilibrium, where the composition varies phase of the system, where there is no taking reaction is taking place. So that is known as equilibrium, chemical equilibrium. When the system is attained thermal, mechanical, and chemical equilibrium, then it's said to be thermodynamic equilibrium. So next, what is the process? A system undergoes from one equilibrium state to another one equilibrium state. So that is the process. Process andre from reaction taking place or anything else from one state to another state. That is known as the process. Here you are taking from state one to state two. The process path may be it will be taking directly, that is the A path, and it may take some time later it will be in the B path. So that process path is known as equilibrium state. The system undergo from one equilibrium state to another equilibrium is called as process. So there are different types of process: isothermal process, adiabatic process, isobaric, isochloric process. So we should these are some important isothermal process is taking place in a system andre where temperature remains constant. Temperature constant temperature irutte system ಅಲ್ಲಿ. So that is the isothermal process. So adiabatic process andre were thermally insulated from the surroundings, where the internal and external of the system will not affect when the system is thermally insulated. That is known as adiabatic process. Isobaric process andre when the pressure is remain constant inside the system. So when the reaction is taking place, you will keep the pressure constant. So isochloric process. Next is the isochloric process where volume remains constant, where there is no addition of atoms or molecules to a system or molecules to the system. And next is the cyclic process, a process which will bring back the system into initial state. State 2 ಹೋಗಿರುತ್ತೆ and return coming back to the state 1. That is uh, called as a cyclic process. And reversible process is one which all the changes occurring in any part of the process are exactly reversed. Then what it is known as reversible process. There is a difference between the cyclic process and reversible process. And irreversible process means where the process is not reversed, cannot be reversible. So that is known as reversible process. So these are the changes of the state of an ideal gas. So isochloric andre where V is kept constant, isobaric where P is kept constant. P is the pressure, V is the volume, and isothermally temperature thermal is kept constant, and isotonic where entropy is kept constant. S is nothing but the entropy of the system. So next is the equilibrium state. One more quasi-equilibrium process where the system adjusts itself internally without showing its process externally. Means remain infinitesimally close to the equilibrium state. So means there is a small changes in the system which can be adjusted itself. That is the quasi equilibrium process. And next is the steady state. Here in the steady state, the process in which the property of the system are independent of time is called as steady state. So it is independent with respect to time. The variables of the system as mass, energy, remains unchanged for the procedure. And next is the work in thermodynamics. So the system work take place inside the thermodynamics. So a system changes from one state to another state. You have seen how the reaction taking place. From one state to another state, it is accompanied by change in energy. So some internal energy changes will take place. The that is measured by joule. So energy changes taking place inside the system is measured by joule. Joule is equal to Newton's meter, where Joule showed that there is definite relationship between mechanical work done and the produced heat produced. So, for example, we are taking one system. This is known as a system where it may be the engines, piston coming inside and outside. That is the for different terms we are labeled. Cyclic process, reversible process, uh, with respect to temperature, what isothermal process with respect to thermally adiabatic process when it is thermally insulated. So these are the different types of the system which we are going to study in the further. And here work is defined as the energy of transfer of a system through change of an external parameters. So work can be studied by energy of transfer from system throughout the change in the external parameters. So when the work is going to take place, the piston moves outside, that the energy extensive parameters can be studied here. So coming to the active area of this is the active area where A is denoted as an active area. This and F is with respect to force and P is the pressure. So dV is equal to AdX, where with respect to volume, A is the active area of the piston and F is the force, P is the pressure. At equilibrium, the external force F is equal to the pressure P. So this is a simple system where you are going to study if there is no work is going to take place, there will be no movement of the piston. So all the force and pressure, everything will be in the equilibrium state. So F is equal to minus PA. And for infinitor, here, infinitesimal process is nothing but it is a small process. So the synonym of this is uh, the small process changes from the position of the wall by dx results the when the piston moves here if it is denoted by dx when the small movement of the piston taking place it can be denoted as delta W is equal to F dx minus P dV. So delta
Sir,
W,
sir, why the negative sign is used here?
where I will tell you in the next, you will get to know in the next uh, slide where with respect to pressure and energy, you will be knowing. I will inform, I'll let you know. Huh?
Okay, sir.
So in this, it is there. Wait, I will let you know. When the piston come inside, it will be in the negative. When it is going outside, it is in the positive mode. So this is the basic. I will let you know in the in the next slide. So that here delta dW is equal to F dx minus PWD, where with respect to pressure, the total work performed, it can be denoted by delta W is equal to V1 integral of V1 to V2 of pressure with respect to volume. So this sign is the work is dependent on the type of the process done. So the compression or expansion, what I have told, the piston is coming inside or going outside. That is the inside andre, it is in the negative, where it is going outside, that is the expansion. So that will be in the positive. So here itself it is there. See, for compression, the work is done. Piston is in negative, where work on the gas. You got it? ಅರ್ಥ ಆಯ್ತಾ? Why the negative sign indicated here? With respect to pressure and active area of the piston.
Yes,
The
sir.
work on
Understood.
the piston is negative. The work on the gas will be positive. So if the piston is coming inside, it will be in the negative. If the piston is going outside, it will in the positive. So it is the oppositely of the work done. So it is in the last para. You go through this.
Okay, sir.
So motion of the piston here, if it is in the the what I explained in the previous, it is in the ಇನ್ನು ಅಪ್ರೂವಲ್ ಪೆಂಡಿಂಗ್ ಎಲ್ಲಾರ್ದು ಆಗಿದೆಯಲ್ಲ ಅಪ್ರೂವಲ್. So here the work done by the system, it can be of initial and final state of the path. So it may depend on the motion of the piston. So piston moves away from the molecule during the collision. Molecule lose kinetic energy and thus do the work that is in the positive. So these are the two different system, which is motion of the piston moving inwards and outwards. So next is an heat in an thermodynamics. So energy is transferred in a system in the form of heat when no mechanical work is done. So energy can be transferred from a system A to B without doing any work. So if it is kept together, the energy of the system from one, that is heat, from a temperature of a system A can be transferred to the temperature of the system B. That is what heat in thermodynamics without doing any mechanical work means. If the piston is not moving, also if it is kept, the temperature can be moved towards both the system from A to B system. That is the heat in thermodynamics. Next is the heat capacity. So heat capacity is the system absorb an amount of heat. So heat capacity that varies with respect to temperature. Therefore, the value is also considered on the narrow. So 1 degree centigrade, it may be depends as the temperature increases, the capacity of the heat of the system also varies here. So this is with respect to heat capacity. And heat capacity, there are two types of heat capacities. One is heat capacity at constant volume. Heat capacity with respect to constant pressure. Keeping constant volume, the variation of the heat can be studied, and keeping the pressure constant, heat capacity also it can be studied here. The heat supplied to a system to raise its temperature. So it is nothing but the temperature rise in the temperature of 1 degree Celsius, keeping the volume constant. So same as it is for pressure also. The heat supplied to a system. When the heat is supplied to a system through 1 degree rise, means the temperature of the system is raised by 1 degree. So keeping pressure as the constant, that is known as heat capacity at constant pressure. So here is the brief review of the thermodynamics. Coming to the zeroth law of thermodynamics, here if a body of A is equilibrium with body C, and the body of B will be equilibrium with body C, then the body A and B also will be in the equilibrium state. That is what the zeroth law of thermodynamics states. So if a system A is equilibrium with the B and B is equilibrium with the C, A and C are also in the equilibrium state. So that is what the zeroth law of thermodynamics states here. And next is the first law of thermodynamics, where energy can neither be created nor be destroyed, although it can be transferred from one form to another form of the energy. So that is the first law of thermodynamics. And the mathematical formula for the first law of thermodynamics, where delta E is equal to Q minus W, where this the delta E is nothing but the internal energy of the system, and Q is the quantity of the heat, and W is the work done of a system. This is the formula for the first law of thermodynamics. Yeah, what you said, why the energy is in negative. I told it will be coming in the next, right? Yeah, this is the energy. If the heat is evolved by the system, it will be in the negative. Positive means heat is absorbed by the system. When the heat is absorbed by the system, it will be in the positive. When the heat is evolved by the system, it will be in the negative side. So next work, the work is done by the system, that piston comes inside andre work done tane. So if it goes outside, it will be in the negative. So that is what the positive and negative sign indicates here. The equation can be written for small changes. If d is equal to dq minus dw, or it can also be written as minus dq, taking on left hand side, dq is equal to minus dq is equal to d plus dw. That is the equation 2. Q is nothing but the quantity of heat. So with respect to system, Q is greater than 0, means the heat of the system is more than 0. It is in the positive. When the W is greater than 0, the work is in the done by the system. So heat is in negative when Q is less than 0, when it leaves the system. So work is in negative andre W is less than 0 andre, that is work is in negative when it is done of the system. Now you got to know about the positive and negative sign of the system. So these are the changes in the internal energy with respect to state functions. So with respect to pressure, volume, and temperature. So next is the enthalpy or heat constant. Enthalpy is the thermal change at constant pressure. Most convenient expression in the terms of enthalpy. So, what is the difference between the enthalpy and entropy? Hmm? Enthalpy is the sum of internal energy and pressure, time, volume. So, entropy is the measure of system's thermal energy per unit temperature. So, entropy is nothing but we are going to measure the system's thermal energy. So, it is denoted by S, and enthalpy is denoted by H. H is the enthalpy, E is the energy produced by the system, which is inside the system, and P is the pressure, V is the volume. So, therefore, change in enthalpy means enthalpy of the product means enthalpy of the system changes means enthalpy product minus enthalpy of the reaction taking place. If you subtract, you will get the change in enthalpy. Enthalpy is nothing but the sum of internal energy and pressure, time, and volume. So it is denoted by H is equal to E plus PV. So next, delta H is equal to H2 minus H1 andre the system which the reaction taking place. ಈಗ for example from H1 in the H2 ಆಗಿದ್ರೆ you are going to subtract to get to know the delta H. Delta is nothing but the enthalpy of the system. So to calculate the enthalpy of the system, you are going to subtract the enthalpy of the second system minus first system. So this is what they are given in the equation 4. So H1 and H2 are the enthalpies of the system. Yeah, they are given. And H1 and H2 are the enthalpies of the system 1 and 2 respectively. So if you calculate further, H1 is equal to same as it is in the equation 3. What is they given? H1 is equal to E1 plus PV1. H2 is equal to E2 plus PV2 of the system 2. So if you want to calculate delta H, you are going to subtract. The final equation is delta H is equal to delta E plus P delta V plus V delta P. That is equal to delta Q plus V delta P. If you substitute this, you will get the equation of. And next is the mathematical representation of the heat capacity. So here we are going to calculate the heat capacity of the system. So the mathematical representation where C is the heat capacity and dq by dt is the quantity of heat with respect to temperature. T is with respect to temperature here. So it is from the first law of thermodynamics. So in the previous you have studied the first law of thermodynamics. Here they are given the equation delta E is equal to Q minus W. So that we have taken delta Q is equal to delta E plus P dV, where if you are going to substitute this equation in the dq, the equation dq, we are going to substitute this, where we will be getting the equation C is equal to delta E plus PdV. PdV is with respect to pressure and volume of the system by delta T. That is the equation 7 for the mathematical represent the calculation of the heat capacity. So next is the heat capacity of the system at constant volume By here in the further, we are going to keep some of the constant and we'll be calculating with respect to constant volume, with the respect to constant pressure. uh, we'll be getting the deriving the equations. So in the system, we are going to calculate all the terms, uh, keeping it temperature constant, pressure constant, and volume also constant. We are going to vary other variables. So here in the first, heat capacity of a system at constant volume. By keeping volume constant, we are going to calculate the heat capacity of the system. So CV is the heat capacity is equal to dE by dt, where the equation, there is the equation 8. So next, with respect to heat capacity of system with respect to constant pressure. So previously we have derived what is the heat capacity. So keeping pressure constant, pressure ಈಗ in the 1.7.6 heat capacity of a system at constant volume andre, where the volume will be 0, same as it is for constant pressure andre, where the pressure will be kept, P will be 0. That we are going to calculate, represent the expression. So here Cp represent the specific heat at constant pressure, and dH is the change in enthalpy, and dt is the change in the temperature. So we should be knowing the difference between delta H and H. So H represent the enthalpy, delta H is the change in enthalpy. So same as it is with respect to temperature also. T is with respect to T represent temperature, and delta T represent change in the temperature. So this is the difference between delta and normal variables. And next is the relationship between constant pressure and constant volume. So we are going to express the relationship. So by taking the previous what we have taken for keeping the heat capacity for constant volume, ಈ expression ಬಂದಿದೆಯಲ್ಲ, this we are going to take with respect to constant volume, heat capacity with respect to constant volume, and this is the heat capacity with constant pressure, that we are going to take it here, and we are going to express the relationship between the constant pressure and constant volume. So Cp minus Cv, that is the equation 13, that we are going to solve from the equation 8 and the equation 12. And this is the mathematical derivative. Let's go through this. And next, we'll be getting, after substituting Cp minus Cv, we are going to get the equation where there is the 16 delta V by delta T with respect to pressure into delta E by delta V with respect to temperature plus pressure. If you substitute, you will get to know. ಈಗ ತಗೊಂಡಿದ್ದೀರಾ ಈ values, these variables should be substituted. Constant Cp, constant pressure minus constant volume. You're going to build the relationship here. And next, for keeping ideal gas as constant, ideal gas delta E by delta V with respect to temperature, that is 0. If you are keeping ideal gas as a constant, we will be substituting that as 0. ಈಗ delta E by delta V with respect to temperature ಏನಿದೆ in the equation, this will be 0. After the substitution, you will get the equation 17. That is what delta remaining is delta V by delta T into pressure. This is the equation 17. For 1 mole of ideal gas, the equation can also be written as PV is equal to RT. So this with respect to temperature at constant pressure, we are going to differentiate for 1 mole of ideal gas. This is enough. If you get the equation 16 for the next ideal gas, keeping constant with respect to temperature, they don't need only the relationship between the constant pressure and constant volume. Till 16, if you're going to write, that's enough. And here, delta Q is the amount of heat that is given to the system, and delta is the change in the internal energy. So this is with respect to relationship of the constant pressure and constant volume. Next is the second law of thermodynamics. Here it helps to understand the direction in which energy can be transferred. The second law of thermodynamics helps in the understanding the direction of energy. So the energy has been transferred. So it helps to predict whether the chemical reaction um, helps us to predict whether a chemical reaction can occur spontaneously. So what does the second law of thermodynamics states here? It is important to construct a heat engine which is operating complete cycle. So we'll abstract heat from a single body or convert the whole of it to work without leaving changes in the work system. So when the system is constructed, it is important to completely shift or completely operating from state one to another state. So that is very much important, and complete converting wholly the work without leaving any changes in the work system. That is the second law of thermodynamics. Work can always be converted into heat, but the conversion of heat into work is taken place under these conditions. So second law also deals with the concepts of entropy. Entropy, what does the entropy is the measure of system thermal energy per unit temperature. So next is the concepts of entropy. Entropy means the measure of system thermal energy per unit temperature. So entropy is the quantity which tells us whether the chemical reaction or physical change can occur spontaneously in the isolated system. So entropy is denoted by S, and next delta S is the change in the entropy, and delta Q is the amount of heat absorbed by the system. So entropy is an extensive property. Since it depends on the mass of the system, the entropy is defined only in terms of delta S is equal to delta Q reversible by T. T is nothing but with respect to temperature. Thus, the change in entropy of the system is the amount of heat absorbed reversibly by the system with respect to temperature. So, what are the physical significance of the entropy? Andre importance, physical characteristics important is of the entropy. Entropy is real physical quantity. It remains constant if the substance undergoes reversible adiabatic comparison. So there are two types here. Entropy is measure of unavoidable energy. Uh, what are the energies produced in the system can be measured, and one more is the entropy and disorder. So it is a measure of disorderness of the random of the system. So it can also measure the randomness of the system. So these are with respect to entropies. Entropy is nothing but you should be knowing the concept of entropy here, the measure of a system thermal energy with respect to temperature. So that is with respect to entropy. And next, what are the silent features of entropy? Andre, entropy defines microscopically in the same as defined as macroscopically. So macroscopically ಏನಿದೆ delta S entropy and with respect to temperature, that is what in the microscopic. So entropy of a system is also a state function. So therefore it is denoted by S, and those are the silent features given here. And next is the surroundings are much larger than the system. So the process is carried out very slowly to ensure the good heat exchange. These are the silent features where the process should be carried out very slowly to ensure the good heat exchange. Heat exchange is nothing but the measure of a system with thermal energy. So next, these are the important terms you should be knowing. And next is the combined form of first law and second law of thermodynamics. So after combining of the first law and second law of thermodynamics of this equation, we are going to get one more expression here. That is the equation delta E is equal to T delta S minus P dV. So in the from the mathematical expression of the first law of thermodynamics, what it says here, dq is equal to d plus dw. That is the first law of thermodynamics, and from the second law of thermodynamics is the delta S is equal to dq divided by temperature. So it can be written in the form where dq is taken on the left hand side, T into delta S. So that is the equation 27. That is nothing but the mathematical step of second law of thermodynamics. So if you combine those, we will get an equation for the equation 26 and 27. T delta S is equal to delta E plus P dV. So this is the equation what you're getting after the after combining the equation 26 and 27. And next is the concepts of fugacity. Fugacity andre ಏನು here? It is an effective potential pressure. So it is an effective potential pressure which replaces the mechanical potential pressure. So fugacity is a pressure like quality that is used to treat free energy of a non-ideal gases. So fugacity is a pressure that likely quality that is used to treat the free energy of the non-ideal gases. And it is nothing but expressed effective pressure having the dimension of the pressure. So fugacity is nothing but the effective potential pressure. So F denotes the fugacity and psi into P, where psi is the fugacity coefficient and P is with respect to pressure. So here we are going to the ratio of fugacity can be calculated to the pressure. So G is equal to H minus Ts. That is the G is nothing but the Gibbs free energy. H is the enthalpy and S is the entropy of the system. So Gibbs free energy in the next it is coming. So in the previous in some of the terms the area it has been explained. So G is nothing but the Gibbs free energy. There are two types of free energies. One is Gibbs free energy and another one is Helmholtz free energy. So here for the Gibbs free energy, the equation is G is equal to H minus Ts. After setting the fugacity equation, so G is equal to E plus PV minus Ts. So by differentiating here, delta G is equal to delta E, the work done after a system. So it can be denoted as delta, and delta G is equal to delta E plus PdV plus VdP minus TdS S delta T. So that is the equation 31. But TdS T delta S is equal to delta E plus PD delta V. That can be substituted in the equation 31. This T delta S value has been substituted in the equation 31. Further, it can be written as delta G is equal to VdP minus SdP. Wherever delta E plus PdV is there, this equation we are going to take it as T delta S. Wherever delta E plus PdV is there, that one we are going to denote it as T delta S plus VdP minus T delta S plus minus S delta T. Where further, where we are keeping temperature as the constant, and then dt will be 0. Where for this equation, if we keep temperature constant, this SDT will be whole 0, and further it can be written as delta G is equal to VdP. That is the equation 32. Uh, Same as it is for the system consists of 1 mole of an ideal gas. PV is equal to RT. So substituting the volume in the equation 32. So PV is equal to RT andre V is equal to RT by P. So wherever the V is present, we are going to substitute by RT by P. That is the equation 33. Further on integration, we are going to get G is equal to RT ln of P plus C. That is the equation 34, where here G represent G1 and G2 are the molar free energies of the gas state in 1 and gas state in the 2. So G is the molar free energies, that is of gas state 1 and state 2. And next, the equation 35, that is what the equation 35 with respect to gas state 1 and gas state 2. If you want delta G, the molar free energy of the gas, total in energy consumed that can be calculated by substituting G2 minus G1. The state of gas state in the G2 minus gas state in the state 1. That we are going to get the equation in the 36. So next is the significance of the fugacity. So fugacity here is nothing but the potential pressure. So what are the importance of that fugacity? So it is considered as a liquid which is in the equilibrium with its vapor. So considering the liquid with the equilibrium with its vapor, when it is kept in the pressure, the fugacity is nothing but the effective potential pressure with replaces with mechanical potential pressure. So the molecules of the liquids tend to escape into vapor phase, where the molecule forms vapor phase tends to back to liquid phase. So here two state from state 1 to state 2 and state 2 to state 1. That is the molecules converts from a liquid to vapor. That is the state 1 to state 2 and vapor to liquid form. That is state 2 to state 1. So mu represent the chemical potential and F represent the fugacity. So here mu is represented as the chemical potential taking place in the system. When these two tendencies are equal, then the system is said to be in the equilibrium state. What in to when these two tendencies are from liquid to vapor, vapor to liquid state, when they are in the equal, the system is said to be in the equilibrium. So that can be represented here. Mu is equal to mu is nothing but the chemical potential. So chemical potential can be calculated by M is equal to mu is equal to RT ln of F plus C, where F is the fugacity of the system. So the chemical potential of two states here also can be calculated. The chemical potential of two states where state 1 to state 2. So mu 1 and mu 2. Same thing, it will be whatever the 1 in the state 1, it will be in the represented as mu 1 is equal to RT ln of F1 plus C, and for the state 2 it is represented as mu 2 is equal to RT ln of F2 plus C. So to determine the chemical potential mu2 minus mu1, where RT ln of F2 by F1, that is the equation 45, to calculate the chemical potential of the fugacity. So next is the spontaneity of entropy and enthalpy changes. Uh, Here some of the reactions are spontaneous in direction of lower chemical potential. So there are two factors which determine the thermodynamic favorability of the spontaneity. So one is the enthalpy change and another is the entropy change. So what is enthalpy here? It is the sum of internal energy. So enthalpy is the sum of the internal energy and pressure, time with volume. So what is entropy change? Entropy change andre the measure of system's thermal energy. So you are going to measure the system's thermal energy per unit temperature. So whatever the temperature changes, that is known as entropy change. So next is the enthalpy change, and the enthalpy change is denoted by delta H. H is only enthalpy change, and H is enthalpy, and delta H is denoted by enthalpy change. Enthalpy change is equivalent to difference in the sum of internal energy with respect to pressure, volume, work, energy of the reactant of the product. So that is the enthalpy change. Here it can be written as delta H of the reaction is equal to sigma summation of delta H naught product minus delta H reactant. So if you are going to substitute, you are going to get the enthalpy change of the system. Reactant in the product form ಆಗಿರೋದನ್ನ subtract ಮಾಡಿದಾಗ you will get to know the enthalpy change. So next, where delta H is less than 0, the reaction is exothermic. So here is the important point. If the delta H is less than 0, excuse, after calculating the delta H, the value of delta is less than 0. The reaction is in the exothermic, and if the delta is greater than 0, it is in the endothermic reaction. So next is this is not enthalpy change, it is entropy change. 1.10.2, that is enthalpy in the spelling typo error, that make it as an entropy change. So entropy is denoted by S. S is entropy, the measure of system's thermal energy. So here entropy of a thermodynamic function, where the increasing as the number of energetic equivalent ways of arranging components by degrees of freedom. And that is what entropy is, nothing but the increasing the temperature of the system, where the calculation of entropy change can be calculated by delta S system is equal to delta S reaction is equal to delta S system under systemal reaction ಆಗಿರೋದು. So again the delta S reaction, the summation of S naught product minus S reactant. If you will get the delta S, the entropy of the system. So if the delta S is less than 0, the process of the final condition may be in the random, then the initial condition. It is an favorable entropy. So if a delta S is less than 0, the process in which the final condition more orderly. So it will be in the orderly state. So this is ಸೌಂಡ್ ಕೇಳಿಸ್ತಾನೆ ಇಲ್ವಾ? ಟೆಕ್ನಿಕಲ್ ಇಶ್ಯೂ ಇರ್ತಿದ್ರೆ ಮಾತಾಡ್ತಿರೋದು ಕೇಳಿಸ್ತಿಲ್ವಾ? ಸಮ್ ಟೆಕ್ನಿಕಲ್ ಇಶ್ಯೂಸ್ ಅಂತ ಮೆಸೇಜ್ ಮಾಡ್ತಾ ಇದ್ದೀರಾ? ಓಕೆ ಓಕೆ, ಹೇಳ್ತಿರೋದು, ಥ್ಯಾಂಕ್ ಯು. Some are messaging technical issue ಅಂತ. Okay. So with respect to, next is with respect to entropy. If the delta is greater than 0, the products are more in the random state. So the formation of the product will be in the random state. So entropy is if the system thermal energy is greater than 0, the products are more random in state and going from solid state to less order liquid. So or less order gaseous state. So either zero in the, if the temperature of the degree increases, the solid becomes liquid, and further liquid will be converted into gas. This is the point that I explained. And next is the increase in temperature. If delta S is greater than zero, the temperature also increases. So solid dissociate into ions upon dissolving. So yes, you got delta S and the entropy change. Entropy change is nothing but the system thermal energy. So these are the points where delta S is more than zero. So here further, reversible or cyclic process, irreversible or spontaneous process. There are two types of process, and third one is non-spontaneous process. The change in entropy is zero, means delta S is zero. That is the reversible or cyclic process. Cyclic process ಅಂದ್ರೆ ಏನು, reversible process ಅಂದ್ರೆ previously we have explained the terms. Go through that. Again, we should be going to that. And here, irreversible or spontaneous process, where delta is greater than zero. So it cannot be reversed. So the process, the reaction will be taking spontaneously. If the delta is greater than zero, means the temperature increases, the reaction will be taking place. So that is with respect to irreversible or spontaneous process. And next is the non-spontaneous process. For a non-spontaneous process where delta is less than zero, it will be in the non-spontaneous process. There is no temperature applied to a system, then it will be in the non-spontaneous process, depending on the entropy of the variables of a system. So, so here, how the entropy, by varying the entropy, how the system varies has been studied here. So that is what entropy on variables of the system. So from first law of thermodynamics, we know dq is equal to reversible dE plus P dV. So T capacity at constant volume. Constant volume andre V will be zero. So with respect to volume, the equation 65, that is dq reversible uh, is equal to Cv of dt plus P dV. So with respect to constant volume. And next, for 1 mole of ideal gas, the equation can be PV is equal to RT, where P is equal to RT by V. So this is an equation for ideal gas. So that we are going to substitute in the place of P in the equation 65. So where the P can be denoted RT by V into dV. From the second law of thermodynamics, we know ds by dq reversible by T, or it is not given in this form. You can ಯಾವ ತರನಾರು ಈಗ temperature ಬೇಕು ಅಂದ್ರೆ you can keep it on left hand side and ds will be in the denominator. So here we need ds is equal to dq reversible by temperature. So or it can also be written as T delta S with delta Q reversible. So substituting the value of delta Q here, whatever the values you are going to substitute. In the place of delta Q reversible, it can be written as T delta S, and CV is equal to CV delta T plus RTB, whatever the equation 66 that has been written. Further, for the different system S1 and S2, same as it is, we are going to write 1 for the system 1 and 2 for the system 2. Substituting the delta S to calculate the delta S, we are going to substitute from system 2 to system 1. That is the equation 68. Further, the equation of for the 1 mole of ideal gas to enter and find the final state are P1 V1 is equal to RT1. So 1 mole of ideal gas to enter and final state PV is equal to RT for initial state. P1 V1 will be in the RT1 will be in for the so here sorry we have taken two different states. Okay. So for 1 mole of ideal gas when added for two different system P1 V1 for is equal to RT1, that is the equation 69 for the state 1, and P2 V2 is equal to RT2 for the equation 79, that is for state 2. So here we are going to divide the equation 70 by equation 69. So I will get the equation 72. Substituting the value of equation 72 in the 68. So whatever the values we have got volume, we are going to substitute that equation in the 68. In the delta S is equal to S2 minus S1 ಇದೆಯಲ್ಲ ಇದು this one we are going to substitute where the volume V1 V2 this we are going to substitute, and further this is the equation what we are getting, and further after substitution Cp minus Cv at constant pressure minus constant volume, that is the R. Or further the equation it can be written by substituting the 74 in the 73 equation where Cv is equal to Cp minus Rc constant volume. Wherever the constant volume is there, we are going to substitute. So that we will be getting the equation 75. This is with respect to entropy on variable system. So next is the entropy and probability. So again, entropy is the measure of system's thermal energy. So here a system tends to change spontaneously from an order state to disorder state. So entropy, the quantitative relationship between the system entropy S and probability can be written as S is equal to S is the entropy where S is equal to minus K ln of W. So it is the spontaneous change from order state to disorder state. And next, the K is the Boltzmann constant, and the W is the probability. So entropy and probability, the equation can be written as S is equal to minus K ln of W. So next, entropy changes for an ideal gas at different process. So by here, the entropy changes for an ideal gas depends upon the condition at which the change in entropy is calculated. So change in ideal gas, it depends on the condition at which the change in entropy is calculated. At what temperature has been calculated, we are going to measure. So there are isothermal process, isobaric process, and isochloric process. You should be knowing what is isothermal. isothermal process, isobaric process, and isochloric process. So these are the important terms explained in the previously. So next is the entropy change in ideal gas in isothermal process. So isothermal process ಏನಾಗುತ್ತೆ? You are going to keep the temperature constant where temperature is 0. So you are going to measure the entropy change by keeping temperature constant. So T2 by T1 will be 0. And for the equation 75, what we have got, this is the equation from where you have got this delta S. Delta S is been calculated for the entropy of the variable system. So delta S for this equation 75, we are going to calculate by keeping temperature constant. So that is the isothermal process. Isothermal process is nothing but we are going to keep the temperature 0 and we are going to calculate from the equation 75. This is the equation where T is present. We are going to put 0 and further the equation 77 we are going to get. And next is the entropy change of an ideal gas in isobaric process. So in isobaric process, we are going to keep pressure 0. So pressure will be in the constant. We are going to measure the entropy change in the ideal gas system. So same equation 75 you are going to take in the previous 75 equation number 75, that you are going to put P is equal to 0 and you are going to get the value. And next is the isochloric process where volume of the gas remain constant. So entropy change of an ideal gas in isochloric process. So here the volume of the gas is kept constant, means V is equal to 0. Same V is equal to 0 we are going to insert in the equation 75 and calculate the, we will be getting the equation 79. So next topic is absolute entropy or standard absolute entropy. So entropy, you're knowing what is entropy, the measure of system thermal energy per unit temperature. So that is the entropy. So standard absolute entropy is the sum of all the entropies it would acquire on warming from absolute 0 to particular temperature. That is the standard absolute temperature. Standard absolute entropy andre the sum of all the entropies it would acquire on warming from absolute 0 to particular temperature. So that is the standard absolute entropy. So here it can be thought a degree of randomness in a system, relative distribution of energy with the system. So degree of randomness of the system andre when the temperature increases, the molecule get dispersed and the randomness occurs. So that is the first point. And next is the relative distribution of energy within the system. So for example, if we take a perfect crystal at absolute 0, means absolute means it will be in the 0 Kelvin as minimum entropy, because each atom in the crystal is locked and fixed in the position. So when the temperature, when you are not giving any temperature to a system, it will be in the 0 Kelvin. Temperature may be in the 0 degree. So if the temperature is kept, there will no randomness of the atom taking place. So that is the example given here. The randomness of the system is lowest in the minimum. So the perfect crystalline solid is zero at absolute zero. That is what they explained. The atoms of the molecules will be in the random. So will not be in the random. It will be in the system where each atoms in the crystal is locked and fixed in the position. There will be no randomness. And next, when the temperature is greater than 0 Kelvin by varying two different equation has been substituted derived here. When his temperature is greater than 0 uh, and entropy is greater than 0. That is what from 0 S is entropy. S 0 to T means 0 to highest degree of the temperature. St minus S0. That is what you are going to get in the equation 80, and with perfect crystal size where 0K 0 from 0 to S naught. It can be written as St minus 0. That is what the St. So entropy of the system of the crystal at temperature Tk. That is what they have denoted here. And the temperature K is nothing but it is represented in the Kelvin, and P is the pressure here. Next, standard entropy changes where delta S naught is the system, and the standard entropy when the reaction involves the reactant and product in their standard state. So the entropy changes, it's said to be standard entropy. So when you consider A moles of A plus B moles of B molecule gives C moles of C product plus D moles of D product. So here the entropy change of the reaction is represented by delta S naught of the reaction my is equal to CS naught of C, where it's simple. If you need to explain in the simple basic terms, Andre, where the product minus the reactant. So that is what they are given in this equation. Thus, delta S naught reaction is equal to summation of N delta S naught product minus reactant. That is in the next step. So where delta S naught is the standard entropy of the reaction, N is the number of moles of the product, M is the mole number of the reactant, S naught product and S naught reactant. It is the standard entropy of the product and reactant. So here are some of the general rules were given. In the gas phase, there are more microstate than in corresponding liquid or solid phase. So in the gas phase, there will be more microstates comparatively to liquid or solid phase. So if the reaction produces more gas molecules in the product, then the reactant, it can be denoted as delta S naught reaction is greater than 0. If the reaction produce more gas molecules after the completion of the reaction, if the product formed where the contain more gas molecule, then it can be denoted as delta S naught reaction greater than 0. And the reaction produce less gas molecule in the product, then the reactant delta S naught is less than 0. So if there is no net charges on the gas molecule, then it can be equivalent or 0. Here some of the worked example where calculate the standard entropy change of the reaction. So this is the reaction taking place in the system where nitrogen plus hydrogen forming ammonia giving. So delta S naught is the, see, I have told in the previous class where they'll give you simple problems where they are given delta S naught. That is the delta S naught ಅಂದ್ರೆ ಏನು? The standard entropy of the N2 ಅಂದ್ರೆ reactant, and delta S naught H2 also is an reactant. Delta S naught NH3 is the product form. So this is the 193.0 K joules per Kelvin mole. So you are going to take this formula for the calculation for the entropy change in the system. So the system entropy, the reaction here, the in a system, the reaction is taking place here is the, this is the reaction taking place. So we are going to calculate the entropy changes. For that, delta S not reaction, and in a reactant to the, and the product value also is there. You are going to substitute that values in this formula. You will get the answer. So that minus 99 joules per Kelvin mole. So next one more is there. ಇದು ಇನ್ನೊಂದು, calculate the standard entropy change for the reaction of calcium carbonate. Here same formula, this one you are going to take again whatever the joules per moles, reactant ಯಾವುದು product ಯಾವುದು, this one is the reactant and these two are the product form. So there you need to insert the values what they are given. You are going to calculate the standard entropy. These are the simple problems which may given. And next is the concepts of free energy function. So here the sum of entropy change of the system and the surrounding serves as a criteria for spontaneity of the feasibility of process. So the concepts of free energy function. Mm, here there are two such types of function introduced. As I have told previously, here Helmholtz free energy and Gibbs free energy. So we'll directly come to the Helmholtz free energy. What does the Helmholtz free energy is defined? Here A is equal to E minus Ts. A is nothing but Helmholtz free energy. E is the energy minus T into S, where temperature into entropy. For small changes, this is the general equation. For small changes in the system, it will be denoted by delta, where delta A is equal to delta A is equal to delta E minus T delta S. It is for the small changes in the free energy. So by definition, the change in entropy is equal to, further it can also be written as delta S is equal to Q by T. T delta S is equal to, when T comes to the numerator in the left hand side, T delta S is equal to Q. Substituting the value of T delta S, we get T delta S ಗೆ Q ಅಂತ ತಗೊಂಡ್ರೆ, we can write delta A is equal to delta E minus Q. According to first law of thermodynamics, delta E is equal to Q minus W. Therefore, delta E, its Q comes on the left hand side, can be written as delta E minus Q is equal to minus W. And substituting the value, we get W, the value substitute, delta E minus Q is nothing but A, that is the Helmholtz free energy. It can be written as delta A is equal to minus W. For reversible, it will be in the maximum state, Austin. And next in the delta is the entropy change, that the energy lost is given by, if the entropy changes, the energy can be lost. So it can be given by dq is equal to dq reversible into T into delta S. That is the equation 48. So here the energy is called Helmholtz free energy, or it can also be denoted as work function. So here there are two types of free energy. One is Helmholtz free energy and Gibbs free energy. And next is the Gibbs free energy. It is the energy available to do work in a thermodynamically closed system at constant pressure and temperature. So it is nothing but the energy available to do the work in the thermodynamically closed system. So it is also defined as energy available during the useful work. So when a system changes from one state to another state, the net available energy of the system under specified condition is decreased in the form of Gibbs free energy. So net energy of the system will be decreases where one system changes from one state to another state. So that is what the Gibbs free energy says here, and it can be denoted by G. G is for Gibbs free energy, and G is equal to H minus Ts. H is the enthalpy and T is the temperature. S is the entropy of the system. For small changes, it can be denoted by delta. When small changes taking place in the system. So further it can be written as delta G is equal to delta H minus T delta S. So substituting the values, you will get delta A same as it is. You are going to substitute and you can get the delta G value. Next the topic one. And next is the significance of Gibbs free energy. So here the three important thermodynamic state function. One is enthalpy change, entropy change, and Gibbs free energy taking place. Significance of Gibbs free energy andre what are the importance of Gibbs free energy anta. So the chemical reaction is governed by three important thermodynamic state function. One is enthalpy change, that is denoted by delta H, entropy change by delta S, and great Gibbs free energy change, that is delta G. So next, the change in Gibbs free energy for an reaction is related to change in enthalpy delta H and entropy, that is delta S. The relation can be written as delta G is equal to delta H minus T delta S with T. So there is a column where you're going to express how the reaction is taking place, whether it is spontaneous or not. So or non-spontaneous the reaction in a system. So sign of delta H, sign of delta S, sign of delta G andre you should be knowing the terms of that. So delta H is the enthalpy. So enthalpy is negative means delta S is entropy. Delta G is the Gibbs free energy. So the enthalpy is negative in the first line where the enthalpy is negative, entropy is in the positive. then delta G is always negative. So the reaction is spontaneous at all temperature. So next is that is the exothermic reaction. In endothermic reaction, delta H will be in the positive, that is the enthalpy, and delta S in the negative, that is entropy is in the negative state, and delta G will in the free energy, that is the in the positive state. The reaction is non-spontaneous at in all temperature. This is for your reference. And next is the exothermic reaction and endothermic in the positive endothermic and positive exothermic reaction taking place. So the reaction is in spontaneous at low temperature. Reaction is in non-spontaneous at high temperature. So with respect to positive increase in entropy, the reaction is non-spontaneous at all temperature. So next, in general, to conclude this delta G, the Gibbs free energy, delta G is less than zero. The process is spontaneous. If the Gibbs free energy is in less than zero, then the process in spontaneous process. If free energy is greater than zero, the process is in non-spontaneous process, and free energy is equivalent to zero, then it has been in an equilibrium state. Whatever the it comes equivalent to zero, it will be in the equilibrium state. So the difference between the Almonds and Gibbs free energy, they are given in the two column. So it gives maximum total work obtained from the system. So by Almonds free energy system, we can give the maximum total work obtained by the system. You can calculate, and further in the Gibbs free energy, it gives the net work obtained from the system. So whatever the basic obtained network obtained by the system, it can be calculated by Gibbs free energy. It includes all kind of works. It includes work other than mechanical work. So these are the two differences, and it originates from internal energy of the system. It originates from the enthalpy of the system. So A is equal to E minus Ts, and here in the Gibbs, G is equal to H minus Ts. So the relationship between Helmholtz and Gibbs free energy, we are going to find the expression for this. The relationship between Helmholtz and free energy, Gibbs free energy. So both the equations we are taken in the 49 and 50. That is what Gibbs and Helmholtz free energy equation. So that we are going to form the equation where substituting the value of H in the equation 49, we get G is equal to E plus PV. And further, that is G is equal to A plus PV from the equation 51. There is the relationship between the Gibbs and Helmholtz free energy. And next is the Helmholtz free energy with and useful work. So considering a isothermal, reversible isothermal change from instant state 1 to state 2. So the elements free energy in the state 1, that will be represented in the 1, and the state 2, it will be represented in the form of 2 for the elements free energy. So that further we are going to substitute delta A is equal to delta V minus T delta S, where we are going to subtract A1 and A2, will get the value of delta A, that is with respect to elements free energy for useful work. So next, for the Gibbs free energy, With the useful work Gibbs free energy equation, we are going to take delta G, the work done get delta we are going to insert. Delta G is equal to delta A plus P delta V, that is the equation 56. And further, we are going to substitute the equation 51 in 52. So this is what the relation what we have got from Gibbs free energy and Almond's free energy relationship that we are going to substitute. And further, the mathematical expression are given here in the equation 59. So this is with respect to Gibbs free energy and useful work. And further, relationship between energy change and spontaneity. So here some of the relationships are there. And next is the delta S and spontaneity. Means delta S is the entropy with spontaneity in the system, and delta G with the spontaneity of the system. We are going to see delta G is with respect to Gibbs free energy. So the Gibbs free energy and spontaneity, where it can be for first one we will be going delta S, that is with respect to entropy and spontaneity. Here we are going to calculate the product minus reactant, that is delta S will be in the negative. Product is less than reactant. So the formation of product is less than reactant. So delta S will be in the negative for the Gibbs and spontaneity. So the equation delta H is equal to delta G is equal to delta H minus T delta S. And so next, where delta G is negative, the reaction is feasible. Where delta G is in positive, the reaction is not feasible. And delta G is in zero means reaction is reversible. So these are with respect to spontaneity of the reaction. And next, if there is a two driving force, the energy changes and the relation can be disorder. So the Gibbs free energy G is equal to H minus Ts. For that, the relationship is spontaneous. In the previous what we have got, the spontaneous K delta G and the spontaneity. We are going to take that equation and substitute. With no mathematical expressions, you can get to know how they are substituted from the previous equation. So next, same, we are going to take one more reaction where A moles of A reactant plus B moles of B reactant forms the product C moles of C product and D moles of D product. So it can be free energy delta G can be less than 0, then the reaction is said to be delta G is less than 0. So that is what they are given, and the reaction said to be in non-spontaneous. And if it is above the reaction, delta G is greater than 0, then it is an reversible reaction. Then delta G is equal to 0, then the reaction is in the equilibrium state. Next, standard free energy changes. It is defined as equal to change in free energy with the reactant. So we are going to study the standard free energy with delta G naught, where it is the initial gives free energy. The free energy changes this delta G naught is the free energy change the results when 1 mole of compound is formed from the constant of the standard state. So delta G naught is summation of delta delta G naught of F product minus delta G naught reactant. So here it is the calculation of standard free energy of the system. So delta G naught is defined as the free energy change at the 1 mole of the compound is formed from the constituent elements of the standard state of the 1 atmospheric pressure. So here we have taken one example by taking 1 mole of the compound. So 1 mole of the compound we have taken and kept at 1 atmospheric pressure in 25 degrees Celsius in the room temperature. So that is denoted by delta G naught, delta G of naught. So that we are going to calculate same as it is for previous what you have calculated delta G naught. Same product minus reactant, you will get the free energy liberated. So that here they are with the example they are given. And next, so some of the examples of the reaction in the system, the reaction taking place, they are given. For methane with oxygen combined from carbon dioxide with 2 moles of water. And one more example they are given, magnesium oxide forms manganese plus dioxide, 2 moles of oxygen. So it can be where how you are going to calculate the delta G naught reaction andre this methane plus oxygen will be taken as the reactant and formation of the carbon dioxide and water molecule is taken as the product. So if you are going to take it whatever the product minus here the react, it's a general product minus reactant, you will get the free energy of that system. So those are the examples given. Next, one more reaction they are taken calcium carbonate and they are given one more calculation. And next is the Gibbs-Almond's equation. So combining of this, you are going to get the Gibbs free energy and Almond's free energy are going to form the Gibbs-Almond's equation. So we can derive this Gibbs-Almond equation with the fundamental equation of Gibbs free energy and Almond's free energy. So delta G is equal to VdP minus SdT, where dP the pressure will be constant, so it is 0. Further the equation 86 it can be written. So in the Gibbs free energy G is equal to H minus Ts. So further it can be written in the equation 87. If you substitute this in mathematical expressions, you go through this, you'll get to know. And the equation 90, this is the Gibbs-Almond's equation. So that is G delta into G by T by delta T with respect to pressure. Next class idea. So H is equal to T square. So here I will explain some another few concepts are there. Can other two will make it fast. So this is the endothermic and exothermic reaction take place as the temperature increases. You can see the plot here. As the temperature increases, the slope you can see here delta H naught increases. So here, as the temperature increases, delta H decreases. So enthalpy of the system decreases here. So enthalpy of the system increases andre that is the endothermic reaction. Endothermic is the chemical reaction in which the reactant absorb heat energy and form the surrounding from the product. So that is the endothermic reaction. What with respect to exothermic andre chemical reaction that the reaction reduces the energy forming the exothermic. So that is delta H naught is less than 0. These are the two plots. And next, the application of Gibbs free energy. So here you are going to see the applications of Gibbs free energy. How we are going to three applications: calculation of delta H and delta EV. When delta G and delta are given at two temperatures, the equation can be used for calculating the variables of the reversible cell, EMF of the reversible cell. So what are the applications of Gibbs and Almond's equation? They are given here. You go through this and example of Gibbs Almond's calculation. So here for an example of Gibbs Almond's equation, they have taken one reaction and they have calculated the Gibbs Almond's free energy. So this you are going to even know, you will get to know what the reaction, what is the reactant and the formation of the product taking place. So hydrogen plus oxygen here gives 2 moles of water. So how you are going to insert the values of this. So for example, grip free energy at 500 K is valued at 290 K 8 Kelvin. So delta G naught will be 500 and one more will be delta G naught will be in 298 K Kelvin. So this is what they applied in this. And next, the compounds of delta H naught per hydrogen joules per mole they are given, and the formation this is the reactant and this is the product. Productal ಎಷ್ಟು joules per moles form ಆಗಿದೆ. So for this you are going to calculate the free energy. Product minus reactant. So whole thing will be this with respect to delta H with respect to Herman's free energy and delta G is with respect to Gibbs free energy. If you subtract the product, the water, what you have got the product, you are going to subtract with the reactant. That is what they are done here. You will get the delta H and delta G. That is the free energy of Herman's free energy and Gibbs free energy you are going to get. Further, you can calculate the Gibbs free energy and Helmholtz free energy. Here. Both have been calculated. And this is the end of this unit. And summary of the unit to that. You go through this, you'll get to know what is the whole basic concept of this unit. And further, zeroth law. If again, zeroth law, first law of thermodynamics, second law, these are the important things what you should be knowing before getting into the next derivations. So enthalpy, heat capacity, entropy. Entropy is the measure of randomness. Enthalpy is the sum of internal energy, and fugacity, spontaneous, non-spontaneous process. And this is the end of this unit.